Okay, so first up, we've got Professor Colin Barrow. Colin Barrow is a Deakin Distinguished Professor and Chair of Biotechnology at Deakin University. His research focuses on food, agriculture, and marine biotechnology. He is the director for the Centre for Sustainable Bioproducts and a program leader for Marine Bioproducts CRC. He's a Clarivate highly cited researcher with more than 300 peer-reviewed publications with over 30,000 citations and a H-index of 83. He's a current member of the ARC College of Experts and also a member of the TGA Advisory Committee.
What the fuck?
Sorry?
That's okay, Del. Somebody was unmuted. I just muted them.
And also a member of the TGA Advisory Committee on Complementary Medicines. So we welcome Professor Colin Barrow, who'll be talking about his initiatives that Deakin University is involved with in organic waste processing to develop a circular economy. So thanks, Colin.
Thanks for organising it all, and also obviously for inviting me. This is the first one that I've been involved with. So hopefully you should be able to see my slides. So I'm going to talk about not just what we're doing at Deakin, but some of the cross-university and also industry partnerships, because I guess in today's research environment, you really have to work as multidisciplinary teams, and I'll talk a little bit about that. So it's a little bit of a strange title, New Paradigms in Organic Waste Processing. I guess the key areas is talking about taking organic waste, and a lot of people don't like the word waste because one person's waste is another person's input material. So taking that organic waste, using it as input material to make products, which is obviously a part of the circular economy, which I'll also briefly touch on. So in terms of research, I like to try and fit research within the UN Sustainable Development Goals, which I think most of you would have heard of. There's two goals that this research mostly fits into, which is goal 12 and 13. So responsible consumption and production. Under that, there's actually a sub-goal of decreasing food waste by 50% by 2050, I think it is. And this is, Australia signed up to this, and a lot of other countries have as well. And there's thousands or millions of tons across the world of food waste. And when I think of food waste, even though the numbers here are just really edible food, it's also agricultural byproduct. So when you make a food, there's often an inedible portion. All of that is really biomass that's available to make products out of. And when we're talking about products, so on the right-hand side, I mean, the worst case is it goes into landfill. If it goes into landfill, then it contributes to methane emissions and also relates obviously to climate change. And so if you can avoid it going to landfill and move it up this sort of destination chain into higher value applications, then you're actually helping with climate action, which is Sustainable Goal 13. So if you look at Australia, and you can look at this with lots of countries, especially agricultural intensive countries, there's a lot of organic resources available, but there's also a lot of demand for organic materials. So for livestock, crop production, agricultural production, they're multi-billion-dollar industries. There's a lot of animal feed, fertilizer, and aqua feed, as well as other materials required. And it's just sort of simple concept is, if you have a lot of crop waste, then you have to dispose of it. It's becoming more expensive, and obviously it can cause methane emissions if you bury it, which is often what happens. If you can take that and produce fertilizer in Australia is actually, a lot of it's imported, and the price has gone up something like 3 to 5-fold. So if you can take your organic material, make fertilizer out of it, you're really solving two problems for farmers at the same time. So the Green Chemistry Centre, which I'll touch on, which is really the organiser of this event, and Tony Paddy, who's the director of the centre, is online. It's a centre where a group of us have got together, tried to apply green chemistry to manufacturing problems. And my main area, as I mentioned, is around organic materials into products. We have a number of, or 6, actually, I've just shown 5 partners here. So just briefly, the type of projects. So Green Ecotech's a company that sells a machine called Wastemaster. They have it in hotels, hospitals and so forth, and you put your food waste in it, it dries it, sterilizes it, which is obviously good in hospitals. And then our project is to try and make products out of it rather than have it go to landfill. And people buy the machine because you get rid of 80% of the waste. So if they do dispose of their waste, they're paying a lot less anyway. So it's actually a good model. Somebody's paying for the drying, then we're taking the material, trying to make products. Another partner is Manzaras Fisheries, who sell a range of seafood products, including calamari, which is squid, and the squid gut as a waste material. So we're making oil out of that. And Ridley's Australia's biggest rendering company. So again, we have beef, chicken, and so forth on the supermarket shelves. You really have to get rid of the waste product, and you can't just dispose of it. You have to make other products out of it. And this has been around for a long time, and most of that goes into animal feed and aqua feed. So we've been looking at, in this project specifically, the colorant in salmon, adding that to aqua feed, which is a compound called astaxanthin, which is quite expensive, and stabilizing it. Another company makes antioxidants, which is Kemin. It's a US company actually, to stabilize food products. Then HiQ, I'm going to talk a little bit about too. This is sort of an interesting area. It's taking waste material and making traditional products that are made out of like petroleum and so forth, which is clothing. So the product they take, or the material they take is cellulose, which is abundant in a whole range of organic materials. One of the most abundant polymers on Earth. And they make infinitely recyclable textile or fiber out of it that can make clothing. And if you think about the circular economy, there's sort of two aspects to it. One is repurposing waste, but the other is redesigning materials so that they can be recycled. And clothing is very difficult to recycle, and it causes a lot of environmental problems. So if you can make it out of cellulose and recycle it, that's a significant move forward. And Haiku's actually commercialized this product. So that's sort of examples, and as well as across universities, our universities set up some initiatives. One is a new centre called the Centre for Sustainable Bioproducts, which really is trying to link academics together to apply a range of complementary technologies that are required to take a biomass and make a product. And then we've set up something called the Deakin Biofactory, which is really a pilot plant for testing processes out. And this is some pictures, just sort of the concept. So we've built this, again, with Monash is involved, RMIT, so it's multi-university. Lisa, who works for me, I put her in some of the pictures for scale so you can see the size of things. But essentially you've got biomass in, you can dry it, there's freeze dry, spray dry, so forth. There's the two series of equipment, one on the left-hand side of the slide, the Waste Master, but there's another one that's 4 tonne a day food waste processing that's been installed. And then on the extraction side, there's things like ethanol and supercritical extraction. And that equipment that we have was actually designed for medicinal marijuana, but you can actually apply it to anything. And then there's a big glass thing on the right-hand side, which is for distilling the solvent off, say, when you do ethanol extraction. And you sort of see if you're training in one area of green chemistry, you can learn a lot of other things. So when we bought this, which was recently, the last group to buy it was a gin manufacturing company. So they're using it to make gin. We're using it to remove ethanol. Then there's some specialized equipment that we've built on the right-hand side, a collagen pilot plant and oil processing units. So the concept really of this, and sort of in general, is you've got a range of input material that is waste or underutilized biomass. Then you put it for a biorefinery process where the waste master can be part of that, or it can be standalone. Then you make a range of products for different industries, fertilizer, feed, cosmetic ingredients, but biomaterials and even pharmaceutical type products can come out of this process. And some things that you wouldn't think about, taking apple material, and you can do calculations, and we've actually turned it into bioplastics. So bioplastics is a very interesting area, and we're spending a lot of time in this area now, because plastics actually comes from petroleum. And if you're decreasing the use of petroleum, which we're hoping to do, then you have to replace plastics with other material. And obviously, plastics are difficult to recycle. They end up in the oceans, and we all know the problems they cause. So if you can make bioplastics out of food waste, it's obviously a nice thing to be able to do. So just in terms of circular economy, So the concept, I think, we talked about plastics. So if you take things out of the ground, in this case, petroleum, which goes into cars and so forth, there are also a whole bunch of byproducts and other products are produced, a whole range of things like plastics. And then the plastics are made and then they're used and then discarded. And you can't just keep doing that. And you can't do it particularly when over the world, wealth is increasing and consumer spending is increasing. So the use of these materials is increasing. So we need a different model. The simple model really is the circular model, where instead of discarding it, we recycle and reuse. But it's not quite as simple as that for a whole range of reasons. And one of those reasons is some of these things are not very easy to reuse. So that's what I said before. It's not just reusing materials, it's changing the way we make those materials so they can be more readily reused. And then if you apply circular economy to an industry, and this is a publication from CSIRO, which is a government organisation in Australia, you're really looking at a whole range of linked things. So when you farm, say, cows, you get methane. That's one problem, but you also get manure, you get abattoir waste, you have water contamination and so forth. So you really have to try and link these things together. You've got to try and produce food. If you can use some of the material waste products for energy, then obviously new products, as I said, from waste material. So cow skin can be made into collagen, for example, but there's a whole range of other blood products and various other things. Then the manure makes really good fertilizer because it has the right sort of components of fertilizer. But if you can take the manure out of the water, then you also get clean water. So there's a whole circular economy concept here, which really you can apply to an individual industry. And then some of the other projects, we're working with company Viva Energy, which is a large petroleum company looking at alternative fuels. So they're actually taking oil waste, including rendering oil, and making biodiesel from it. Then the jet system I showed before, which is the second or the largest of the two food processing systems, that's can take a range of input materials and make products out of it. I won't go into this too much. And then the other thing I guess I wanted to mention is the Dell mentioned about Marine Bioproducts CRC. So it's not just waste material, it's underutilized material, or even material that you can produce, say, through fermentation, such as microalgae, or you can collect like seaweed that has a lot of value in it that's not necessarily utilized. So conceptually, this first generation is fishing, second generation aquaculture, third generation is you still do the fishing and aquaculture, but you produce marine bioproducts, and there's a lot of potential value as a new industry. So we have a large, what's called CRC, which is a 10-year initiative, 270 million over 10 years, with a large amount of money, I think 60-something million from industry partners to do work in this area. So there's 3 programs. So I run this, what's called Innovative Bioprocessing Technology Program, which is producing the products. And the concept, I guess, that I'd like you to get out of it is this concept of biorefinery, which you can call it, some people call it integrated biorefinery, which is really taking a biomass, whatever that might be, and producing a range of products out of it of different value where there's no waste, and each product offsets the cost of the other. So if you take biomass and try and make fuel only out of it, it doesn't work because of cost effectiveness. But if you can make some high value chemicals and other byproducts out of it, and then a certain component of it goes to fuel, then the fuel can be produced at much lower cost and the whole system makes sense. So this is really an example. Take fish waste, you can get enzymes, you can get omega-3 oil for nutritional products, you can get protein for a range of purposes and so forth, collagen. And we're trying to create what we're calling these blueprints, which I won't go into, but they're really methods for doing all of this. And you can start to do, this is with a fish, you can render the fish, or you can, and this is from New Zealand, or you can fillet it and have the waste go to rendering. There's a value to that. But if you took the waste material or even the whole fish and divided it into individual components, there's actually a lot more dollar value in that. So at the very least, you should be taking the waste products, the skin, for example, for collagen. Collagen's, once you've refined it, is quite an expensive material. So a couple of other projects, I guess, of interest, or a few other projects, is looking at seaweed. So seaweed has a range of interesting materials, and one of the areas that's quite interesting is it was found that cows in Canada, actually, a couple of people in Canada in the organising committee here, it's in Atlantic Canada, they were eating seaweed because the paddock was on the ocean, and they were growing bigger than the cows in the next paddock. And it turned out they were producing less methane, and the methane was being converted to meat. They found out the seaweed, Asparagopsis, has a compound called bromoform in it that inhibits methane production. So there's an important discovery, not necessarily just because of bromoform itself, but it shows that cows that essentially burp methane, they can burp much less methane. So that wasn't really known, that you can actually make that change. So now there's other products on the market to do this, but this is where science is essentially helping to solve an environmental issue that isn't necessarily believed to be solvable. So I think I do have certain faith that climate change can be solved, or at least partially solved through research, and this is one example. So we've been working on Asparagopsis in Australia, and this is sort of a seaweed biorefinery concept. So we're working with a company, they take the bromoform out, and then the rest of it goes in towards other product development. And our area primarily is this other product development. And this is sort of a generic slide where if you take the seaweed, this is with a few different companies. I can't show exactly because it's confidential, but we've essentially taken the waste product from the seaweed. We're making surfboard fins out of it, which is this bioplastic concept. We're also making art paper, and the cellulose from some of the seaweeds is going to HiQ for their textiles, and then there's bioactive polysaccharides. There's some very interesting bioactive polysaccharides, and we're making materials for tissue engineering. So it's amazing what sort of things can come out of these types of input materials that you wouldn't think about. And one of the projects I thought might be interesting to show is we're actually taking the seaweed material that we're making bioplastics out of, and we're making three-dimensional scaffolds. And this is actually funded by BP, which is a big oil company, to try and regrow seagrass. So to regrow the seagrass, you need these three-dimensional structures that stop the seagrass being washed away. So there's support, but they need to be biodegradable, and you need to be able to tailor the biodegradability. So we're tuning the biodegradability so the seagrass grows to a certain stage, and then this washes away and doesn't form bioplastic type material in the ocean. So it is interesting what projects sort of come out of the woodwork when you have a technology. And I'll just finish off with a couple other projects. They're not necessarily mine, but they're in the centre, and they're ones that are being done at Deakin. So one is actually recycling tyres and producing green hydrogen out of it, and that's actually a $26 million project. So some of these projects are quite big, with most of that invested from the industry partner. That's an engineering group run by Bass, who's a key member of my centre. And there's another CRC that just got funded, and it's actually solving plastic waste CRC. And I did talk about plastic waste. Manu Miyabi, she's a director. I'm the director of the Centre of, as I mentioned, Sustainable Bioproducts. She's the deputy director, so we work quite closely together. So she's now a program leader for essentially finding out, well, developing new products from plastic waste. So we've been working together on a few different things. One of those is actually, she does carbon fiber work, is to try and make carbon fiber out of food waste. There's a big carbon fiber research facility at Deakin, and carbon fiber is used for a range of materials, but it's not very environmentally friendly, really. It's really good in terms of fuel efficiency, and so that from that perspective, it's great for environment and planes and so forth. But if we can make it from food waste, obviously that's going to be a lot more circular. And then just the last project I'll mention that we're just starting actually is there's a company called Sampara Eco that has an enzyme technology for degrading fibers from clothing, and then we're working with them to essentially rebuild those up into fibers for clothing. So it's very similar to HiQ, but a different type of technology. And they started with an enzyme that could digest plastics, and now they're moving into polyesters and so forth. So that's my last slide. I think it shows sort of the range of projects you can get involved with within the green chemistry area. Sounds good.